Hi folks, today's episode, the microcontroller tutorial series, is on how to use the bitwise operators in the C language we've taken a look at in the previous episode in a way that actually makes sense, or at least kind of sense, because what we've seen in the previous episode, yes, that's the syntax and that's how it works, but that doesn't mean it's a good idea to have these things spread all over your code and expect that things are still readable. The bitwise operators are hard to read in a lot of cases, and the best thing we can do is try to come up with a syntax that is reasonably convenient and to isolate these things to where we actually need them. There are a number of ways to do this. There are a number of misconceptions a lot of people have when it comes to compilers. So I'm just going to give you a show of different things. First thing, previous episode we've seen expressions or statements like this, where we set bit 5 in our variable a to 1. Nothing new about that. And what you frequently see people do is things like this. So they turn this expression here into a constant, or even using hex, or if they really want to make your code hard to read, a decimal. Okay, using a decimal at this point is just atrocious. This is not an accident, this is done on purpose. If you ever see that, it's somebody trying to really screw you over. Another word. And if you've done that yourself half a year ago, yeah, we all know what you are. Don't do this. Simply don't do this. And using an expression like this, sometimes you hear novice programmers say, yeah, but that's inefficient. You have to do the computation every time the program reaches that point in code. No. If there's one thing that C compilers have been good at for the last couple decades, is finding constant expressions, evaluating them once during compile time, and then put the constant result into the actual object code. This doesn't get computed. We're not talking some silly, stupid interpreter that doesn't even do this, and even a lot of interpreters deal with this in a sensible way these days. So performance-wise, all these things just return the same object code. So the only difference here is readability. This one isn't nice, but once you get used to the bitwise operators, it's clear what this is about. This, you start to count individual zeros here. Most likely going to miscount them at some point. So this is no good. Really no good. This is almost as bad, but at least a bit shorter. So if you're tight on disk space on your development machine, okay, these days are long gone. And again, decimal is just unacceptable. That's just really bad coding. Next example. So we want to set 2 bits, bit 5 and bit 3. Here we have 2 separate statements. There we combine them into one. And again, we use the binary notation and the decimal. And again, the compiler will, in all likelihood, I haven't seen anything else, optimize these into the same object code. One more thing, by the way, the 0b binary prefix integer notation that only got introduced into C, I don't know, 10, 15, 20 years ago. So if you have a really old compiler, it might actually not know that. In which case you get a compiler error and be told, hey, do this properly, like something like this. Now, the first 2 variants, which one makes more sense is pretty much up to you and what you're doing. The second one is a bit shorter. The first one leaves you more space for adding comments. Your call, really. Either one is okay with me. Really depends on the situation what makes more sense. and your personal preferences as well. Okay, so that's some basic stuff about what compilers do to your code. Next, if you want to get rid of these bitwise operators, and pretty much everybody who first encountered these has come up with macros like this. You use the preprocessor to hide them away. Perfectly fine. Pretty much everybody has done this before. The naming is a matter of personal preference again. All I do is basically, if I want to get a bit, I select that bit out of the word. I personally do like the double negation here, which will ensure that the macro will return either 0 or 1, rather than, for example, if we set bit index to 5, 32 or 0. Or 0 or 32, whatever. This involves, depending on the architecture, it may involve a bit of computational overhead, might get optimized away by your compiler again, but this you actually want to check. By the way, if you want to take a look at your intermediate compiler output, STCC does that by default. It generates assembler code for you to inspect. With the GCC, you need to run with the option minus uppercase S to tell it, please give me the assembler code output. And then you can take a look at things. And no, you don't have to be really intimately familiar with a particular assembly language to figure out what's going on. Just some basic understanding there usually gets you to the point that you understand. When it comes to microcontrollers, the data sheets, they pretty much always start with these are the machine instructions we have, and you can take a look at these if you want to. So I've done a macro here to get an individual bit, setting bit to 1, clearing a bit, setting it to 0, toggling a bit. None of this should be rocket science at this point anymore. If you don't figure out what this is, go back to the previous episode, please. Explain it there in more detail. And yes, this works. Compiler optimization takes care of things because compiler only gets to see things like this here anyway, so we're fine. One more thing about compiler optimization when you use these. You can frequently help the compiler or make even compilers that are not that good at optimizing this stuff do a better job if you just have the set bit, clear bit, and toggle bit macros for the same variable grouped together. Just speeds up or just increases the likelihood that the compiler figures out, oh yeah, I can optimize that. And if anything else, just take a look at the intermediate assembler code output. Yeah, pretty much everybody has done that. Biggest problem is that the preprocessor is basically just doing text replacement, and that sometimes has strange side effects. That can be a bit of a problem. So what we can do is something like this. What we first do is we don't use macros, but instead we write C functions. Doing this as regular C functions is hideously inefficient. Why is that? Setting a bit, clearing a bit, whatever, at least in some architectures, is done in a single machine instruction. Whereas calling a function that does that involves pushing the arguments onto the stack, calling the the function, which then moves some registers out of the way, which then loads from the stack the arguments into the registers, does the computation, saves the result in another register, then restores the original values of the registers, then returns to the calling bit of code, which then has to make sense of whatever it was returned. Performance difference can be easily a factor of 15 to 20. Don't do that. However, with more recent versions of the ANSI language, we can use something that comes back from C++, which is the inline keyword, which tells the compiler, not the preprocessor, but the compiler, please try to replace this inline, basically like a macro, in the code. Don't make these dedicated functions. And here's the problems with that. First, the compiler doesn't have to inline anything. might decide I'm going to turn this into a separate function anyway, which will be a static function only within a single object file. So use the same header file defining these for multiple object files, link them together, you have multiple copies of the same bit of code. Not nice. Can happen if you turn off inline functions. Can also happen if you use GCC and don't tell it with dash dash std equals C11 or whatever to use a reasonably recent version of the C language, because at least with the GCC I've seen that it just ignores the inline keyword, and they get exactly that effect that you don't want, that these things get turned into regular functions. Yet another problem is that, or no, that's not a problem, that's just the difference between the macros here. I've written the functions I use here to manipulate individual bits to a BF type void. They don't return anything, whereas the macros return the word as value of the expression. I've done that because if you return the old value of the bit or the entire word or whatever, and people depend on it, this is asking for trouble when people try to change, update, modify your code. You add a number of hidden dependencies there if you're unlucky that really make it hard to maintain your bit of code. So sticking with voids here in this scenario actually just avoids trouble when it comes to maintainability. And I had to provide some sort of type for the arguments, which is okay. So I've used unsigned 8-bit types for both the index and the word, which is not really a word except on 8-bit architectures in this case. But what if I want to use this on 32-bit ARM Cortex-M based microcontrollers, where the word could be 32 bits in size by default? Then I'd have multiple functions. So I'd have something like get bit underscore U8 for unsigned 8-bit, or U32, or S16 for signed 16-bit integer, whatever. I could do that, but that's where things get a bit awkward. You have basically the same sort of code, and yes, you could use, this is going to be messy, but it's possible you could actually use some serious preprocessor trickery to generate this for you. The other option is go C++ and use function templates, where you make the argument types templates. Yeah, otherwise does exactly the same. Problems here is you need C++. As such, not much of a problem, as long as you do, no. Biggest problem here is that when things go wrong, you're actually confronted with C++ and the sort of syntax it supports. So you need to be kind of familiar with C++ when there are problems with your code. And C++ is a notoriously weird syntax. Other problem is you need a C++ compiler. So if you only have a C compiler, or the C++ support in your compiler is limited, then you can have a problem. Right. And there's a misconception a lot of people have. They think that C++ is less efficient than C. That's nonsense. If I take standard C code, run it through a C++ compiler, it'll be just the same as running it through a C compiler, except for the name mangling, that the intermediate names in the object code, which you're never going to take a look at anyway, will look differently, have to look differently. But the eventual binary executable will be just the same. There are some features in C++ which are inherently more resource intensive. If you use them, you have this overhead. If you use them intentionally, because otherwise you'd have to implement them in C doing things yourself, you don't lose anything. Chances are that the compiler builders knew more about your particular machine architecture than you do, and the output code is actually more efficient than what you would have done. It happens to me all the time when I take a look at what an optimizing compiler produces with assembly code. Not that I look at that often, but still. The only problem is if you use features of C where you're not aware that these are resource intensive and you use them where you don't really need them, yes, then C++ programs get a bit less efficient. But that's not a problem of the language, but that's a problem of yours. So using this actually does make sense if you have a C compiler at hand. Okay, there's that. And then there's something we have to talk about, because good chance you don't even know that these things exist. Back in the old days, when I was a teenager and Kernighan-Ritchie C was the standard C, the one and only C, really, this was already around. It's a feature called bit fields. Works like this. You take a struct, and in there you have various integers. Integer types can be anything. Unsigned int, signed int. Doesn't matter. Most people just use unsigned int for this sort of job. And they say colon and the number of bits in that integer. So these are 1-bit integers, unsigned integers. And the C compiler stuffs them into machine words. Works nicely, saves a lot of memory if you use them right, but Kernighan-Ritchie, from the Old Testament, the first edition, covering Kernighan-Ritchie C, to the, where is it? There is it. I think I've shown that before. Second edition, 1988, covering NZC, explicitly say that the way how these are arranged inside a word is up to the compiler, not you. It's not defined by the language as such. It's really what the compiler does. You change compiler flags, change to a new version of a compiler or change to a different compiler. These things will likely be laid out differently than before. These are really meant for just using them as they are inside memory, and then they're really useful. But if you do something like this, you combine one of these structs with bit fields and some sort of integer into a union, which is basically like a struct, except that all its elements are placed in the same area of memory. What you can do with this is you can access individual bits inside your unsigned char. Problem is, you can't be really sure which pin whatever bit field element is which bit inside the unsigned char. So this might actually, pin 0 might give you the most significant bit rather than the least significant bit of all pins. So you'd probably be well advised to reorder these then. Might actually find out still doesn't work because the compiler for some weird reason sorts these alphabetically or whatever. Using a union in combination with bit fields to access bits or groups of bits inside some sort of word is a decidedly bad move. And the only reason why I actually bring this up is because the header files for the PIC shipped with the SDCC do exactly this. Now this is a border case because they come with a compiler, so you can expect them to work. But just don't copy that idea. And even with the way they've done it, I'm not really happy with it. It's asking for trouble, really asking for trouble. So stay away from these bit fields unless you just want to keep things tightly packed in memory. But don't do this combination of bit fields and union stuff. It's no good. And in case you wonder, yes, I've given it a try. So I've tried to figure out which pin is which. And you really have to try it out, basically, or take a look at the compiler sources if you want. And then there was another thing that I found quite interesting. So I said, what's the size of such a union? And if I compile this on Raspberry Pi, my development machine, the size of one of these union port things is 4 bytes. The Raspberry Pi is a 32-bit machine, so word size is 32 bits, 4 bytes, despite the fact that you could stuff all this into a single byte. And there goes your saving memory as well. So just don't bother. Good. What else can we do? To be done. Says C++. What's this about? Okay. What I'd like to do at some point, but not right now, is to come up with a, say, a C++ namespace GPIO, where we have in there a class port, and we have another class pin, or maybe pin set, so you can have multiple consecutive pins grouped together, and we have input pins, output pins, and we could actually tell the port, okay, I need pin so-and-so, and the port object would keep track of which pins are actually used for what. The constructors would make sure that output pins are initialized as output pins, whereas input pins are initialized as input pins, and so on. Could do all sorts of strange things with that. If we were writing some big proper program, that'd be a really smart thing to do. Problem with microcontrollers with a couple hundred bytes of RAM is you really want to be careful how this works out memory-wise and code-wise and performance-wise in general. And the reason why I haven't even tried it at this point is we've only talked about output so far. And this should actually support input pins as well. And we haven't talked about that, but we should know about these before we start to write a library. Writing libraries is notoriously difficult anyway, because you have to be very careful what assumptions you make. Try to minimize the assumptions you make. And if you don't yet know about the intimate details of how these work, microcontrollers, it just doesn't make sense. It's just going to be big, unwieldy, and the API will be inconvenient to use. And then you add some features that are more convenient, which will add to the code load. And that doesn't make sense. When you write a library, start figuring out everything you need, everything you want to do, and only then start to actually come up with an API. And I'm not sure if this actually makes sense using a C++ like this on a microcontroller anyway. We'll leave that to a later episode, maybe. There's one more thing, however, and that does make sense, and I've used that when I wrote the first versions of this code that do the LED blink stuff. It looks like this. And if you run this through a compiler as is, you'll get error messages redefining macro blah blah blah, because what's missing here are some if-def and so ons. Basically what I've done here, I've added an abstraction layer, a zero overhead abstraction layer, where I say I initialize an LED, I turn it on, I turn it off, or sets of LEDs. And I just define these at some place in a separate header file or at the beginning of my program. And with that I can make sure if I add an ATtiny13, where you don't want to use bit B5 or pin B5 for blinking, because it's normally the reset pin for programming, so I know I have to change this in this one spot. And all the rest of the code is independent of the particular machine, and with a bit of thought and a bit of work you can actually write your code such that it compiles for various PICs, various atmals, various MSP430s without actually changing the code. Yes, you'll eventually get the if to hell if you have to support too many architectures, but then you split that off into separate header files that are reasonably straightforward to maintain, and then you're done. And then you actually get no-cost portable microcontroller code. We're going to take a look at these things another time as well. Important thing here is that this doesn't try to solve the problem of making all code portable to all sorts of architectures. It's specific to my LED blinking program, and it's specific to the architectures I've used. But you have to know which pin your LED is connected to anyway. So yeah, this is something I strongly advise to use. Okay, that's it for today. Hope you found it interesting. And yeah, just keep your cone easily readable, easily maintainable with this sort of programming style. I wouldn't even want to call it technique. Hope you liked it. If you have comments, questions, whatever, as usual, come to the forum at www.stepladder-it.com/BIVBlog/47 and hopefully see you again soon. Bye.